Welcome back to the Foundry by Forge College. I'm super excited you're joining us for today's explainer, Data Management Fundamentals in Firedancer. Now, if you caught our last session, you know we covered interoperability and the impact architecture has on Solana throughput. We learned that batching and parallelism are, honestly, absolute lifesavers when it comes to reducing lock contention. But today we're looking under the hood. We're moving away from high-level architecture and getting right down into the actual pipes and plumbing. We are going to map out exactly how a Firedancer validator manages, moves, and stores the massive flood of data it has to handle every single second. So grab your hard hats, maybe a plunger, because we are diving straight into the plumbing.
Okay, let's dive into our engineering blueprint for the day. First, we'll look at the Firedancer waterworks analogy, then move into intake and filtration, followed by timestamps and reservoirs. After that, we'll hit persistence and treatment, figure out how we're measuring the pipeline, and finally, wrap things up with the optimization workflow.
Section 1. The Firedancer Waterworks. Let's build our mental model.
To really wrap our heads around how Firedancer handles data without getting completely bogged down in abstract code, we're going to treat it like a physical system. Which brings us to the million-dollar question. How do you prevent a Firedancer validator from clogging? Think of a validator as literally a massive industrial waterworks facility. But instead of millions of gallons of raw water rushing in, we're dealing with a relentless flood of data packets. Our main goal here is to move, filter, measure, and store all this data without our tanks overflowing or our pipes completely bursting. If we can understand exactly how the water flows, we can figure out exactly where the pressure builds up. Moving on to Section 2, Intake and Filtration, where we handle the network I/O.
Let's start right at the very beginning of our pipe network. This is where the raw material first hits our system from the outside world. Our intake valves here are the network receive buffers, and these have two absolutely crucial parameters: how fast the raw packets are arriving, and how much temporary holding capacity we actually have. It's pretty simple, really. If the raw network water rushes in faster than our internal pipes can handle it, these intake valves have to throttle. If they don't do that, the packets just queue up, overflow the capacity, and literally spill all over the floor. And you know, in networking, a spilled packet is a dropped packet. Dropping packets is basically like pouring money down the drain. It just completely ruins our throughput.
Once that water is inside, it needs to be cleaned up. That's where our deserialization workers come in, acting as our first layer of heavy filtration. These filters use really intensive CPU cycles to inspect every single drop. It's actually amazing how this works. They completely strip out the malformed or malicious entries, the, digital mud and rocks, if you will. And they transform those raw payloads into a clean canonical format that the rest of the validator can actually use.
Section 3. Timestamps and reservoirs. This is how we measure the flow.
So, the water is in and it's been filtered. Now, as we move deeper into our facility, we need to talk about how we measure this flow and where we store it while it's waiting for processing. This brings us to proof of history, or POH. I want you to think of POH as a highly precise cryptographic flow meter. It stamps an ordered sequence and a specific time onto the data passing through. This is absolutely vital because it gives all the downstream workers a completely stable, perfectly synchronized order. They know exactly what sequence the water arrived in, which means they can process it all in parallel without needing to constantly stop and talk to each other to coordinate.
After passing the flow meter, the water moves into our holding reservoirs. In Firedancer, these are in-memory buffers. We're talking fast, lock-free queues for the super hot paths, meaning the water never has to stop at a toll booth. We've also got per-core staging buffers for parallel replay, where multiple lanes can process data all at once, and reorder buffers to sort out any packets that happen to arrive out of sequence. But a quick warning here, reservoir sizing is honestly an art form. If these tanks are too small, boom, you immediately get back pressure. The water literally has nowhere to go. But if they're too large, well then you just end up masking a downstream leak or a blockage until it turns into a catastrophic problem.
Now, what's really interesting about this concept is the critical difference between these two specific metrics. It's super tempting to just look at queue depth, right? Just the sheer volume of water backed up in the system. But actually, time in queue is a far, far superior indicator of a bottleneck. Think about it for a second. A giant reservoir might hold a massive amount of water without overflowing, sure. But if that water just sits there for ages before moving on, your system is still choking. Measuring how long data waits tells you the true story of your pipeline's health.
Section 4. Persistence and treatment. Time to look at permanent storage.
All right, so the data has been ingested, it's been filtered, timed, and staged.
Let's move all the way to the end of the line, where our treated data gets permanently stored. In Firedancer, this is Cloudbreak. Cloudbreak is essentially our treated water storage facility. It uses what's called a sharded layout, meaning it splits the storage tanks up so water can be poured in and drained out of multiple tanks simultaneously. It's incredibly efficient, but there is a catch. If this treatment plant writes to the disk too slowly, the water has nowhere to go, and that back pressure? It will travel all the way back up the pipes, filling up those staging reservoirs we talked about, and eventually causing massive latency spikes right at the intake valves.
And this brilliantly illustrates exactly what we've just been talking about. Just imagine the linear path a single transaction takes through this whole setup. Millisecond 1, it hits network ingress. Millisecond 2, the deserialization filters clean it up. Millisecond 3, POA sequences it. Millisecond 4, it's sitting in-memory staging. And by millisecond 5, it hits persistence in Cloudbreak. It's just a relentless, high-speed relay race happening in literally 0.005 of a second.
Section 5. Measuring the pipeline. Let's figure out where to install our gauges. Now that we actually understand how the plumbing works and the path the water takes, we need to know exactly where to install our pressure gauges. We need telemetry. A good engineer doesn't just stare at one single dial, right? You need two core telemetry axes here. First up is time series alignment. This lets you overlay different metrics so you can see what happened to the whole plant at exactly, say, 2 p.m. Did a spike in intake match a sudden spike in memory usage? Second is causal tracing. This is where we attach correlation IDs across stages, so we can ask, hey, what happened to this specific drop of water? Tracking it all the way from ingress to persistence.
Let's break down this diagnostic table, because this is how you prevent mistaking a symptom for the actual root cause. If your network IOQ depth is rising, it might just be a network storm. Or your system might be suffering from syscall saturation, which is basically the software equivalent of a bureaucrat demanding way too much paperwork right at the intake valve. If the deserializer has high parse latency while the queue depth is low, your CPUs are choking on the parsing work. If the POH sequencer is showing growing reorder buffers, you've got sequencing pressure. And if persistence has high write latency, well, that's going to cause all those upstream queues to grow. You always have to combine these metrics to find the true culprit.
Section 6, the optimization workflow, how we actually fix system clogs.
Okay, we've got our blueprint, we have our pressure gauges installed. Now here is the exact procedure to fix a clog in the system when you inevitably find one. So the crucial point is this 5-step workflow. You map the handoffs, you define your metrics, you collect your baseline traces so you know what normal actually looks like, then you perform stress tests to break it on purpose, and finally you iterate. This workflow is what converts those vague 3 a.m. panic-driven guesses into precise, targeted engineering interventions.
Once you run those stress tests, your interventions usually become pretty obvious. If your CPU is maxing out during deserialization, well, you just add more parallel filters. If the sheer data volume is too heavy, you can switch to a more compact binary layout to literally shrink the volume of the water. If you need to balance memory against latency, you adjust your pipe sizes, your buffers. And if you're getting back pressure from storage, you optimize exactly how you batch your writes to Cloudbreak.
I love this point because it perfectly sums up the core philosophy of Firedancer data management. Never, ever guess where the leak is without checking your telemetry first. Doing broad, speculative changes, that's just going to cause new problems. You always measure first, correlate the data across the entire pipeline, and only then do you modify.
Which leaves us with this final, really critical thought to ponder. We've built an incredibly fast, highly optimized waterworks facility today. But soon, it's going to have to interact with the incredibly strict, unyielding timing constraints of the network's consensus mechanisms. How in the world do these data flows survive that kind of pressure? Well, that is exactly what we are going to tackle in our next lesson, consensus mechanism integration in Firedancer. If you want to dive deeper into this topic and explore even more incredible Web3 learning programs, be sure to head over and visit forge.college. Thanks so much for joining me on this explainer, and I'll catch you in the next one.